Alright friends, here's that video that I promised you on specific heat capacity. If you were absent on September 1st, that was last Friday, if it's 2023, if you were absent on that day, that was honestly not a great day to miss because we started doing math for the first time in here. And the math is not super simple. It's rather simple, like it's just multiplication and division. But knowing exactly what to multiply by or what to divide by can be a little bit tricky, especially if math is not your strong suit. So, you know if that's you, and you know whether or not this is going to be a trickier unit for you. Um, Not really a unit, but a topic. We'll spend probably like 1.5 to 2 weeks on calculations with thermochemistry. So that will be specific heat calculations, and then we will do some more math stuff probably the second half of next week. But for now, I'm getting ahead of myself. Let's talk about specific heat capacity. You hopefully remember from last week, it was like early last week, I think, I gave you a paper that had told a little story about Maya and Gabby. Maya and Gabby are not cubes, but they did. Maya and Gabby conducted this little experiment where they took these cubes of metal. One was made of iron and the other was made of aluminum, and they put those blocks of metal into some hot water. I think it was boiling water even, and they put them in there for not that long, and then they took them out of the boiling water. And what they were trying to figure out was how much energy, or rather, how did the temperature of the blocks change? Because both the aluminum block and the iron block, when it's put in the hot water, of course, heat is going to transfer from the hot water into the metal blocks. And they noticed that they did not change temperature in the same way. The iron block heated up much faster than the aluminum block. And so we looked at a few factors that were affecting how quickly the metals were absorbing the energy, but the main thing that we need to focus on for this packet here is specific heat capacity, which is one difference between aluminum and iron. What is specific heat capacity? Well, it is basically how hard it is to heat a substance. And every substance, iron, aluminum, water, oxygen, carbon dioxide, wood, plastic, all the different types of plastic, they all have different specific heat capacities. This definition is not very specific, and it doesn't sound very sciencey, does it? So the more specific definition for specific heat capacity is joules per gram degree Celsius, which means the amount of energy. Joules is a unit of energy, by the way. It is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So, for instance, liquid water has a specific heat capacity of 4.18 joules per gram degree Celsius. This right here is 1 gram of water. Maybe it's kind of hard to see where the water is. This is the water. So not very much water at all. That's 1 gram of water. And what that 4.18 number is telling us is that if we want to take this amount of water, which let's say that this amount of water has a temperature of 20 degrees Celsius. If we wanted to heat up the water by putting it on a hot plate, and we wanted to change the temperature from 20 to 21 degrees Celsius, in order to do that, that water is going to have to absorb some amount of energy from the hot plate, right? That amount of energy is 4.18 joules, right? So this is 4.18 joules is like 4.18 joules of energy, that is required if we want to raise the temperature of 1 gram of water by 1 degree Celsius. That's what that means. So 4.18 is the specific heat capacity of 4.18. Don't get tripped up by that word capacity. You might know capacity to be something like how much heat it can hold, or how much liquid a cup can hold. We can say, what's the capacity of this container? This is not really capacity in the same way. You can just kind of forget that meaning of the word. So specific heat capacity does refer to the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Now, if we wanted to raise not 1 gram of water, but 2 grams of water by that same change in temperature, right, by 1 degree Celsius, then how much energy do you think that would require? We got twice as much water now. Hopefully we can see that it should be, it should be double. It should be 8.36 joules. So 4.18 times 2 is 8.36. And that's exactly how much energy is required to raise the temperature of 2 grams of water by 1 degree Celsius. 1C here, see, now we're taking those 2 grams of water and we're going to raise the temperature of those 2 grams of water not by 1 degree Celsius, but by 2 degrees Celsius. So now, like, twice as much temperature change as compared to 1B. Take a moment, think, how do you think this amount of energy should be different from 1B? It should definitely be more energy, right? Because we're doing a bigger change. I'm hopeful at this point that we were able to see that this is going to be just double again. So that's going to be 16.72 joules of energy is required to raise the temperature of 2 grams of water by 2 degrees Celsius. Why don't you try 1D on your own? You can pause the video now and give it a shot. All right, if you couldn't quite get it, 4.18 joules is required to raise the temperature, remember, of 1 gram of water by 1 degree Celsius. 1D, we're asking about 1 gram of water again, but now we're not interested in raising it just 1 degree Celsius. We want to raise that by 10 degrees Celsius, so we're heating it a lot more. In fact, 10 times as much. So if the temperature change here, if that's going to be 10 times as much, then the amount of energy that's required should also be 10 times as much, shouldn't it? So this is going to be 41.8. 41.8 joules of energy is required to raise the temperature of 1 gram of water by 10 degrees Celsius. One E is a little bit different because now we have two things changing here, right? It's asking us about 7 grams of water, which we have not seen before, and it's also asking us about 3 degrees Celsius of a temperature change. And we have not seen that before either. So this isn't going to be as simple as just like multiplying by 2 or multiplying by 10. There's a few things going on here. See if you can figure it out. All right, so before I show you how to solve 1E, I need to show you this method that we use of solving these problems. So let's look at 1B. Let's go back to 1B for a second. We know from 1A that 4.18 joules of energy is required to raise 1 gram of a substance by 1 degree Celsius. Because 4.18, that's its specific heat, right? By the way, if you were absent on Friday, you should really copy this into your notebook. Everything that I'm writing on this notebook sheet right here. So 4.18 joules is the amount of energy that we use for raising 1 gram of a substance, or 1 gram of water, I should say, by 1 degree Celsius. 1B was asking us for the amount of energy that is required to do 2 grams of water by 1 degree Celsius, so twice as much water. We already did this one, so I can do this quickly now. But actually, no, I do kind of want to go slow here. I want you to think about this, everything that's in these parentheses. These parentheses are important, by the way. I want you to imagine everything inside this parentheses is one number, and everything inside this parentheses is one number. In fact, if you want, you can even go in and write in what 1 times 1 is, like above the parentheses like that. And then you can write in what 2 times 1 is, just like that. So 1 times 1 is 1, and 2 times 1 is 2. And then the question that you ask yourself is, obviously 2 is bigger than 1, but how many times bigger is it? Is it 5 times bigger? Is it 3 times bigger? No, obviously it's just 2 times bigger, right? So we multiply, to get from the top to the bottom, we multiply by a factor of 2. And just the same way, we're going to multiply by a factor of 2 to get from the top to the bottom on the left side as well. So this is how we can see that our answer here should be 8.36 joules. We just do 4.18 times 2. So 4.18 times 2 equals 8.36. Okay, that was the easy one, 1B. Let's jump back again to 1E where we left off. Every time you do one of these on this sheet, I do want you to, in your notebook, write out this. You're going to write out 4.18 J, that's 4.18 joules. That is the amount of energy that is used for heating 1 gram of water by 1 degree Celsius. That's what that means. And the question here, we want to know how much energy do I need for raising 7 grams of water by 3 degrees Celsius. So this is more water and a greater change. Well, just like before, I want us to consider everything in this parentheses as one number and everything in this parentheses as one number. And we can even write in our products again. 1 times 1 is 1. 7 times 3, well, that's 21. And now the question that we ask ourselves is, how many times bigger is 21 than 1? Well, of course, it's 21 times. And so just the same over on the left side, I'm going to also multiply this by 21 to get the answer, to get my question mark. So this is going to be 4.18 times 21. And I have my calculator here. This is going to be 4.18 times 21. Gives me 87.78. I'll round that to 87.8 joules of energy required to take 7 grams of water and increase its temperature by 3 degrees Celsius. So that's the answer to E there. One F. Actually, let's skip F for now. Why don't you give G a shot? We'll go over G in a second. All right, so once again, 4.18 joules is the amount of energy that is used to heat 1 gram of 1 degree by 1 degree Celsius. You're going to get tired of writing that by the end of this video. You should be copying along with me, by the way. I know it feels kind of silly, and maybe you think that your time is better spent just watching, but it is actually really important that you do write this down. Otherwise, it's just going to slide right out of your head after you close this video out. So you got to keep it locked in your brain. All right, so this is 4.18 joules, again, used to heat 1 gram of water by 1 degree Celsius. Number 1G was asking about 100 grams of water and 30 degrees Celsius. So bigger changes than we've been looking at before, but nothing we can't handle. So we're going to set it up like this. Once again, we're looking for the the number of joules. And now, just like we've done before, we're going to multiply these numbers up, 1 and 3,000. And we're going to know that 3,000 is 3,000 times bigger than 1. So then whatever this number is should also be 3,000 times bigger than 4.18. So to get my answer here, I'm going to go 4.18 times 3,000. All right, so 4.18 times 3,000 gives me an answer of 12,540. 12,540 joules is the amount of energy required to heat 100 grams of water by 30 degrees Celsius. And there we have it. 1F and 1H are different, because we can see now in 1F and 1H, we are given the amount of energy that's required to do something, and we need to figure out exactly what that energy can do. So give it a shot. See if you can figure out where the numbers go. Set it up the same way I set these up. And then, yeah, you can pause the video and I'll show you in a sec. Okay, so 1F. This time, we know that 83 joules of energy is being used to raise the temperature of some amount of water by 5 degrees Celsius. Let's have 1F here. Once again, we're going to go 4.18 joules is the amount of energy required to raise 1 gram of water by 1 degree Celsius. This time we know it's 83 joules, so I'm not going to put a question mark there. Which, between my G and my C, which one's going to get a question mark in front of it? That's right, this one's going to be a question mark in front of the G, because I don't know how many grams of water I'm dealing with here. But I do know that the change in temperature is 5 degrees Celsius. So now I'm solving for something on this right side over here. Remember that our first step in all these previous ones was to treat the things in the parentheses over here as one number and figure out what those products are. We can't do that in 1F here because I don't know what this question mark is, right? That's what I'm trying to solve for. So I'm always going to start, instead of always starting on the right, I'm always going to start on the side where I have all the numbers, right? So I don't have any question marks over on my left side here. So that's where I'm going to start in this case. And just like I did before, I want to figure out how many times bigger 83 is compared to 4.18. So I know that I can do 4.18 times some number, and it'll give me 83. I just don't really know what that number is right now. To figure it out, I'm going to have to go 83 divided by 4.18. And that will tell me how many times 4.18 goes into 83, right? And in this case, it is 19.86 times. So 4.18 times 19.86 equals 83 joules. Because I wrote an arrow over here, right, and it times by some number, I'm going to always make sure that on the other side of my little system of equations here, sort of, I'm going to write the same arrow and the same number, right? Because that's going to tell me the relationship between this and this number. So now I can say, okay, 1 times 1 is 1. I guess I could have done that before. But now I also know what the product of these two numbers are, right? Because I know that this bottom parentheses has to multiply to be 19.86 times bigger than the product of this parentheses, right? So this parentheses is telling me 1. So what's 19.86 times bigger than 1? Well, it's 19.86, isn't it? So now, this is great. I know that whatever this mass is the mystery number that I'm solving for, times 5 equals 19.86. So that's kind of neat. Now I just need to figure out what that grams is. Well, I know that if there's some number and I can multiply by 5 and get 19.86, I should be able to take that 19.86, divide by 5, right, doing the opposite of multiplication, and it should give me the answer, right, just fine. So I'm going to do 19.86 divide by 5, and it gave me 3.97. Let's go 3.97. That's 3.97 grams of water. And before I just move on from that and like call it a day, let's see if that makes sense. First of all, 3.97, we can call it 4. 4 times 5 should be about 20, right? And we're a little bit less than 4, so that makes sense that we'd be a little bit less than 20. So that's good. When you do your division, it's easy to accidentally mess that up and punch it in your calculator backwards, right? And accidentally punch in 5 divided by 19.86. Or you might not think that that happens, but trust me, it happens all the time. So when you get your final answer, go back and check that your multiplication works out now, right? You should be able to see that, like, your answer, if that's the question mark, you should be able to say 3.97 times 5. You can even punch it back in your calculator, and it should tell you 19.6. If it doesn't, something weird happened. And sometimes you won't even realize that you're supposed to be multiplying to 19.86 because you didn't write anything on your paper. A lot of people will think, oh, that's so much writing, I really don't want to deal with that. But trust me, if you write all this out, you are way less likely to make mistakes. The people who make the silly mistakes on the quiz are the ones who are trying to do it in their heads or do it all in the calculator. Don't do that. There's no reason to. Just put it on the paper. And especially when you're doing practice like this, it does you no good to just try to do it all in your calculator. I know it's very tempting to be lazy. I understand. I get it. But write it out. Write it out. You will learn so much better, and you'll retain it so much better if you write it out. If you just try to do it all in your calculator, it doesn't stay in your brain very long. Okay, you need to like write it down to sort of cement it into your brain. So honestly, if you have not been writing it down and you've just been watching me or like following along with your calculator, please go back and write this stuff down and listen to the words that I explained them, or explain it for yourself. It's really, really valuable that you do that, because otherwise this can be really tricky, and I don't want you to fall behind. All right, you should be able to try 1H now. 1H is just like 1F, but now we're solving for a change in temperature rather than a mass. But the process is exactly the same. So give that a shot. All right, so on this one, 112 joules is required to raise the temperature of 60 grams of water by some number of degrees Celsius. Okay. For 1H, just like for all the other ones, I'm going to start by writing out my 4.18 joules is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. I always start by writing that if we're dealing with water. Right? If we're not dealing with water, we're not going to put this 4.18 number. We'll put some other number. But that 4.18 is specific to water. That's a specific heat capacity for water. The number of joules here was 112 joules. And we want to know what the change in temperature is of 60 grams of water when we apply 112 joules to that water. Okay, so again, I'm going to start on the side where I don't have my question mark. So I'm going to start on the left side again, and I'm going to ask myself, how many times bigger is 112 compared to 4.18? So to figure that out, I'm going to go 112 divide by 4.18, and it's going to tell me 26.79. All right, so 4.18 times 26.79 equals 112. Whenever I write an arrow and a number like that, I'm always going to mirror it on my other side. So over here is also going to be times 26.79. Now I can solve my products here. 1 times 1 is 1. 60 times some number is 26.79, right? Because 1 times 26.79 is 26.79. Remember, this tells us the relationship between this parentheses and this parentheses, right? So this multiplies to 1. 1 times 1 is 1. 60 times something must multiply to whatever 1 times 26.79 is, which we know to be 26.79, right? So this has to multiply to be 26.79. And now to get the question mark, I'm just going to undo that multiplication and go 26.79 divide by 60. Divide by 60, and that gives me 0.45 degrees Celsius, or 0.44 degrees Celsius, I think, depending on how you round it. But less than half a degree, right? And it's not even that much water. It's 60 grams. The thing is, that's not a whole lot of energy at all. And water, right, has actually a relatively high specific heat capacity at 4.18. We're going to look later at some specific heat capacities of metals, and most metals are in like the 0.3 to like 1.5 joules per gram degree Celsius. Water is especially high, and its high specific heat capacity is actually one of the things that makes it so important to us on Earth. Ask me more about that later. All right, so there's 1H. So in summary, to figure out the amount of energy required to raise the temperature of water, the specific heat capacity of the substance should be multiplied by the mass of the substance times the change in temperature. And there is actually a formula that does make this kind of simpler if you are formula-minded. I can show you the formula now, and if when you see all these letters you freak out a little bit, just pretend the formula doesn't exist. I don't think you really need it. Q is equal to M times C times delta T. Let's talk about what those letters mean. The Q means quantity of heat. And you can put in parentheses in joules. It's the quantity of heat in joules. M stands for mass. C stands for specific heat capacity. And delta T stands for change in temperature. This little triangle right here, it's called a delta. That's what that triangle is called. It's actually a Greek letter, D. It's called delta, and it means change in. So delta T means change in temperature. All right, so that's that. So if we're ever trying to solve for quantity of heat, right, the amount of heat that is required or absorbed in order to do something, you can multiply by the mass times the specific heat capacity times the change in temperature. And that is that. On the next page, you will find a very similar table. In fact, it's identical, except for one difference. That is, we're no longer looking at water. The first page was all about water and changes in temperature to samples of water. Now we're looking at copper. Like I said on the first page, and like the first, 2 minutes of this video, all substances, or every substance, has a different specific heat capacity. So copper and water heat up very differently. Remember I was telling you about how most metals have a specific heat capacity between like 0.3 and like 1.5, whereas water has a much higher specific heat capacity. So copper having a specific heat of 0.39 joules per gram degree Celsius tells us that if we want to raise the temperature of copper by 1 gram, if we want to raise the temperature of 1 gram of copper by 1 degree Celsius, that's going to require not 4.18 joules, but 0.39 joules, way less energy to do the same thing. So I am not going to go through each of these examples because the math is exactly the same from 1A through H and 2A through H. It's all exactly the same math. Once you have those figured out, you can like use your notes to figure out the notes that hopefully you were taking to fill in 2B through 2H. Do this in your notebook as well. I'm going to remind you again, don't be lazy. Write it out like this. Write it out like this. It's worth it. It's worth it. I promise you that it's worth it. It'll make the rest of this topic so much easier, and you're making it so much harder on yourself unnecessarily by trying to do it all in your head. I promise that like it's not it's not easier to do it in your head. It's not. In the long run, it's not. It's just not. And also you should practice how to do the work, because on the quiz I need you to show your work, right? Just putting in the answers is not an option. You won't get credit. It's impossible to get a 3 if you don't show me any work. All right. If you have any questions on any part of this, I should have said this at the beginning. If you have any questions on any part of this, I'm gonna try this. Try leaving a comment on this YouTube video, or if you don't like that, send me an email. You have my email, or you can ask me in class, of course. But that is that. I'll be making a second video at some point on these questions. These were the questions that 6th and 7th hour did on Tuesday, September 5th. That was today. 6th and 7th hours did these questions. They made it about halfway through. Everyone else, you will do some of these questions tomorrow, probably as a whiteboarding activity, and then we'll jump into something else. If you happen to be watching this on the 5th or on the 6th, we have a lab on Thursday, so wear closed-toed shoes. Just a helpful reminder. And if you are watching this in 2024 or 2025, or anytime that's not the first week of September, the second week of September of 2023, just, I don't know, ignore all that. This should still be useful for you. I don't know. We'll see. Alrighty. It's been fun, but I need to stop talking or my voice is going to die. Alrighty. I'll see you tomorrow.